So we talked about a pulsar, and the neutron star has to be sweeping this beam of particles and radiation at us for us to see it. And maybe there's neutron stars that don't do this, but we see a lot of these beams and they're correlated with neutron stars. And there's not a whole lot else that they could be. Is all right, we're looking at something where the circumference of the thing is 60 kilometers and the spin rate can be up to 1,000 rotations per second, which means that the surface is moving about 20% the speed of light. And that's about the escape velocity from what we think a neutron star would be. That'd be something like, you know, a few solar mass neutron star. Anything else wouldn't have the sort of density necessary to hold itself together. Is this could only be a neutron star or a black hole, and we can detect the object there, so we know it's probably a neutron star. Right. And again, this is the sort of thing that is that the core would be something the size of the Earth, let's say, or something larger than the Earth, and it's a rotating object. But as it collapses into that dense ball of neutrons, angular momentum's conserved. In this case, it stays spherical, but it speeds up. Right. So neutron stars are also in binary systems, and it would be a really good question to ask what happens to the other star when a star supernovas in these binary systems. But we'll ask instead what happens when there's a neutron star in a binary system. And matter can fall inwards the same way as it does with a white dwarf. Is matter will fall in, it'll form an accretion disk. We can see an accretion disk, and that matter in falling will cause the neutron star to spin up because it'll gain the angular momentum of the infalling matter. And that matter can fall in, and eventually, um, the temperature of the matter on the surface of the star will be high enough for fusion to start. And what we see from it is a burst of X rays, which indicates that it's probably helium fusing and giving off X-rays, producing that, helium fusing to carbon gives off sufficient energy as X-rays, and so we see X-ray bursts instead of nova. They're the same sort of mechanism. In falling matter starts to fuse, but the mechanism gives off X-rays instead of visible light. So we talked about black holes a lot earlier. Briefly, I'll go through it. Uh, Classically, it's just a matter of the escape velocity being the speed of light. And so the matter that's there, you have a potential energy and a kinetic energy. When stuff is sufficiently massive and sufficiently dense, you can reach an escape velocity that is higher than the speed of light. And so light can't escape. Right. And that can be anything. You can take the earth and shrink it down to this, the size of a walnut, and it would be dense enough to turn into a black hole. There's nothing, you know, mathematically, there's no reason why it has to be produced by a star. Though that seems to be the thing that gives you enough force to cause that contraction. So the surface is what we call the event horizon. Where we put it is what's called the Schwarzschild radius. We talked about that. Within the event horizon, you can't see anything. Is events inside of it don't exist in a sense. It'd be about the size of a small city for a 3 solar mass black hole. And the larger the black hole, the larger the radius is. It warps, it has significant gravity, so it warps the space around it. Nothing can escape. You can't see events inside of it. And we figure that there's a limit. Things that are larger than about 3 solar masses have to be black holes. Is that neutron stars are limited by their size by how much gravity can crunch against the degeneracy pressure.